All right, in today's lesson here, we're going to be looking at solving trigonometric equations. The focus here will be on trigonometric equations where either we're compressing that trig function or stretching that trig function out and solving these. So let's take a look at our first example. I've got the sine of 3 theta is root 3 over 2. The domain here goes from 0 to 360. So if we wanted to solve this, again, your first step is you're going to go ahead and take the sine inverse of both sides, giving us the following. So at 60 degrees and 120 degrees, you can see here on our unit circle, at those two values here, you end up getting the sine of 60 and 120 is going to be root 3 over 2. So we can go ahead and write down that 60 degrees and the 120. Divide across by 3, we end up getting 20 degrees and 40 degrees here. Now the idea here is that we're taking our normal sine function and we're compressing that by a factor of 3. Let's take a look at a quick diagram comparing the sine of 3 theta and the sine of theta. So what I have here in red is one cycle of your sine of theta. This starts at 0 degrees, goes all the way up until we hit 360 degrees, or 2 pi. What we have here in blue, it represents the sine of 3 theta, and again, that will continue on all the way up until we hit our 360 degrees, or for this axis here, it ends at 2 pi. So you can see here that one complete cycle of our sine function ends approximately here, then it starts up again, ends, then it starts up again, and ends. So sine of 3 theta is happening 3 times, cycle is repeating 3 times, and the time it takes your normal sine of theta function to complete one cycle, which is 2 pi. So the idea here is now what we have to do is find the period of our sine of 3 theta function. To find the period of the sine of 3 theta, what you do is you take the period of your normal function, sine theta, which in this case, we're measuring this in degrees, so that's going to be, as discussed, 360 degrees, and you're dividing that by 3, giving you 120 degrees as the period of the sine of 3 theta. So we're going to go ahead and add that to our values here, both to the 20 degrees and to the 40 degrees. We'll keep adding the period of the function until we use up our entire domain until we're greater than 360 degrees. So adding 120 degrees to these values gives us the following. Going ahead and adding the 120 to the 20 and 40 degrees, I get 140 degrees, 160 degrees, 260 degrees, and 280 degrees. Again, I added 120 again to these values, and if I do it a third time, we're going to be outside of the domain here, so we stop. So the solution set is as follows. We end up getting here 20 degrees, 40 degrees, 140, 160, 260, and 280. Let's take a look at another example. All right, for the next trig equation here, we want to solve the cos of 2 theta equaling minus a half. And again, we're bounded between this interval. This time they're expressing in radian measure, so our answers have to be in radians. First step is to go ahead and take the cos inverse of both sides, giving us. And you'll see here on our unit circle at 2 pi over 3 and 4 pi over 3, that's going to give us values such that the cos is minus 1/2 here. So we can go ahead and write those down here. We've got 2 pi over 3 and 4 pi over 3. Going ahead and dividing across by 2, I get theta equals pi over 3 and theta equals 2 pi over 3. Let's take a look comparing the graph of cos of 2 theta with the cos of theta. All right, we have here the graph of cos of theta in red and the graph of cos of 2 theta in blue here. And you can see here that your cos of 2 theta function will start at 0 and completes one cycle right about here. Then that cycle starts up again and complete. So you can see the cos of 2 theta in a span of 0, which starts here, all the way up to 2 pi, will complete its cycle twice, whereas the cos of theta requires a period of 2 pi, starting here, continuing all the way up until we hit 2 pi to complete one of its cycles. So the period here of your cos of 2 theta function, to find that, you're going to go ahead and take the period of your normal function, in this case cos of theta, which has a period of pi, divide that by the compression factor, which is 2, and we end up getting the period of cos of 2 theta is pi. So I'm going to go ahead and add the period of the function to both pi over 3 and 2 pi over 3 until we use up our entire domain. And you'll notice here I have my pi over 3, my 2 pi over 3, adding the period of the function, you get 4 pi over 3 and 5 pi over 3. If I do it one more time, we'll be outside the domain. You'll notice if I add a pi to this value, we're going to end up getting 7 pi over 3, which is greater than 2 pi, and we're outside the domain. So your solution set for cos of 2 theta equaling minus a half are these 4 values. All right, let's take a look at another example. All right, in our final example here, we want to solve the tan of theta over 2 equaling the root of 3. And now we're going between 0 and 4 pi. So first step here is same as the previous two. We're going to go ahead and take the tan inverse of both sides, giving us. And you'll see here by taking the tan inverse of both sides, there's two values. You're going to get pi over 3 and 4 pi over 3 for one rotation here. So we've got our pi over 3 and 4 pi over 3. Your tan function will be the root of 3. Now we're going to go ahead and multiply across by 2 this time instead of dividing, giving us 2 pi over 3 and 8 pi over 3. Let's take a look at a graph of the tan of theta compared with the graph of the tan of theta over 2. So taking a look at a graph here, I have in red graph of your tan of theta, and we have a graph of the tan of theta over 2. Notice the tan of theta has a period of pi, and we're going from 0 to 4 pi, so you can see here that we've got one cycle of your tan of theta, a second cycle of your tan of theta, a third cycle of your tan of theta, and a fourth cycle of your tan of theta, which should make sense here. When you take a look at the tan of theta over 2, you can see here it takes this much time here to complete one cycle of your tan of theta over 2. Then the cycle starts up again. So only 2 cycles happen with the tan of theta over 2, as opposed to 4 cycles with the tan of theta when you're between 0 and 4 pi. And that's because we're slowing things down, stretching this out by a factor of 2. So everything this time is going to take twice as long. So if I'm going to go ahead and find the period of the tan of theta over 2, realize that the period of your tan function normally is pi, as discussed. And now we're compressing that by a factor of a half, so essentially dividing by a half, so that period becomes 2 pi. So I'm going to go ahead and add the period of the function to our values that we found already until we use up our whole domain, giving us the following. And right away here you see that if I go ahead and add the period of the function 2 pi to this, right away we're outside of our domain. If I add 2 pi to this, we end up getting 14 pi over 3. But as you know here, we're capped at 4 pi, which is equivalent to 12 pi over 3. So your solution set for tan of theta over 2 is just 2 pi over 3 and 8 pi over 3. All right, that concludes today's lesson on solving trigonometric equations.